Okay guys, so last day you learned about the four quantum numbers. N is the principal quantum number, L is the secondary quantum number, M is the magnetic quantum number, and S is the spin quantum number. N had to be an integer, L ranged from 0 to n minus 1, M was minus L to plus L, and spin can only have two values that are plus or minus 1/2. So how does this break down? Well, in the first energy level, n equals 1, L has to be 0, ranging from 0 to 0. If L is 0, then M is 0, and the spin can be plus or minus 1/2. That means in the first energy level, there's only one sub-energy level with only one orientation that can hold two electrons spinning in opposite directions. That means the first energy level can hold two electrons. What about the second energy level? If n equals 2, then L can be 0 or 1. If L is 0, then M would be 0. If L is 1, then M can be -1, 0, or +1. That means there are four sub-energy levels. One corresponds to the s orbital, and the other three correspond to the three orientations of the p orbital. So that means there's four sub-energy levels, or we call them orbitals now. Each can hold two electrons with negative and positive spins representing spinning in opposite directions. So four orbitals with two electrons each. That means the second energy level can hold a total of 8 electrons. What about the third energy level? Well, if n equals 3, L can be 0, 1, or 2. If L is 0, then M is 0. If L is 1, M can be -1, 0, or +1. If L is 2, M can be -2, 0, +1, or +2. That represents a total of 9 orbitals, or sub-energy levels. Each of those sub-energy levels can hold two electrons spinning in opposite directions, so opposite spins. That means 9 orbitals, 2 electrons each. A total of 18 electrons fit in the third energy level. For the fourth energy level, L can be 0, 1, 2, or 3. M can have these values. Now we have a total of 16 sub-energy levels, again corresponding to S, P, D, and F orbitals. And each of those sub-energy levels or orbitals can hold two electrons with opposite spins, so we get a total of 32 electrons that fit into the fourth energy level. In case you're thinking, why didn't she tell us this? I did. It's right there. Okay? And then just to summarize it further, I gave you this. Excuse me. So again, N refers to the energy level. It does correspond to the period for the S and the P orbitals, but it doesn't correspond to the period for the D and F orbitals. So please be aware that N represents the energy level, not the period. The S orbitals correspond to a value of L equals 0. The P orbitals correspond to a value of L equals 1. The D orbitals correspond to a value of L equals 2. And the F orbitals correspond to a value of L equals 3. For L equals 0, M equals 0. So the only difference between these elements, they'll have opposite spins, plus and minus 1/2. When L equals 1, M can be -1, 0, or +1. So how do we distinguish between these negative ones, these zeros, and these plus ones? We do it using the spin. The first three have a positive spin, the second three have a negative spin. For L equals 2, M can have these 5 values. How do we distinguish between these 5 and these 5? With the spin number. And then for the F block, M can have the values -3 to +3, and to distinguish these 7 from these 7, we just use opposite spins. Okay? So now let's try the worksheet that I gave you. Here we go. Excuse me. All right, so we tried sodium. You guys are all familiar with how to do the electron configuration. Okay? So you could do that with ease. don't worry about the quantum description, we'll come back to that. Here's an energy level diagram. It shows the lowest energy orbitals being filled first. So this is 1s2, 2s2, 2p6, 3s1. So we know the last electron is placed in 3s1. We can use a shorthand notation. Neon is the nearest noble gas. It has 10 electrons, so we only show what's beyond the nearest noble gas. So after 10 electrons, there's only one left, so we write 3s1. The energy level diagram is simply a vertical Bohr diagram. It shows you how many electrons in each energy level. So now let's do the quantum description. The last electron placed was in 3s1. So because it's the third energy level, n equals 3, the s orbital corresponds to L equals 0. If L equals 0, then m equals 0. And because it's the first electron placed, the spin is plus 1/2. Now let's do sulfur. You know how to do the electron configuration: 1s2, 2s2, 2p6, 3s2, 3p4. Here's the energy level diagram, and again I'm lining up all my s orbitals and all my p orbitals vertically, going in an order of increasing energy, so 1s2, 2s2, 2p6, 3s2, 3p4, and watch that the electrons are placed one in each orbital before you start pairing up. Otherwise you might end up with 2 and 2, and that becomes really important when we look at the trends. So we place 1, 2, 3, and there's the fourth electron placed. Alright, what's the shorthand notation for that? Well, again, the nearest noble gas is neon. What's beyond neon? 3s2 and 3p4. Why do we use the shorthand notation? It concentrates on what's in the outer shell, and that's really important for chemical reactivity because chemical reactions only involve the electrons in the outer shell. There's the energy level diagram for it, 286. Let's do the quantum description for it. The last electron placed was in the third energy level, so n equals 3. It was placed in the p orbital, so L equals 1. The p orbitals range in order of -1, 0, or +1. Since it's placed in the first p orbital, that's an m value of -1. But since it was the second electron placed in that orbital, it gets a spin of -1/2. All right, let's make it harder. Let's do molybdenum. It's element number 42. There's the electron configuration, and here's the energy level diagram. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d4. So the last electron is placed in 4d4. Shorthand notation, well, the nearest noble gas is krypton. So we write anything beyond krypton. So anything beyond the 4p6. Okay. So that gives us 5s2, 4d4. Notice how I like to rearrange that to 4d4, 5s2. That makes me aware that I only have 2 electrons in the outermost shell. That's going to be, again, important for reactivity. There's the energy level diagram, just showing how many electrons in each energy level. And then the last one here, we got brave and we did actinium. Okay. The electron configuration for it looks like this. Oops, we started with francium, but we switched it to actinium, so ignore the FR. Okay, so 1s2, and actually let me show you, as I read it out, how this corresponds to the periodic table. So let's look at the periodic table. Okay, and here we go in order. So 1s2 fills hydrogen and helium. 2s2 fills lithium and beryllium. 2p6 fills boron, nitrogen, oxygen, and fluorine, and neon. Okay. 3s2 fills sodium and magnesium. 3p6 fills the next block of p orbitals. 4s2 comes next. 3d10 comes after that. Now, why is it 3d when it's in the fourth period? Because we figured out before that the third energy level has 3 possible sub-energy levels. So when we're filling those d orbitals, they're actually part of the 3rd energy level. Why don't they get filled first? Because it reduces the repulsion to put the electrons, some of them into 4s2, and then continue filling the 3d orbitals. So that first block there is 3d10. Okay, then we get to 4p6, 5s2, then after 5s2 comes 4d10, so again the second d block corresponds to 4d. Then the 5p6s get filled,